addressing schemes and VLSM, which is an interesting concept. So for planning a network addressing scheme, we can separate it, as we talked about, by different departments. So part of the network administration process is planning out a network. How are we going to address it? How are we going to group it together? Addresses should not be assigned randomly. There should be a purpose and a structure to it, because network addresses are supposed to help us identify something about that computer, the type of device that it is, where it's located, what it does. So how many subnets are going to be a part of that structure? How many hosts are needed for each subnet? As we went over last time, you know that the subnet mask is the thing that determines that. So it tells you about the network, how many hosts and how many subnets are available. Which host needs a static IP, which ones can use DHCP. That's all part of the things that we plan with the network. So the things that need a static IP are servers, printers, maybe switches. They might need a static IP. So we need to stop and determine when we're planning our network those kinds of things. When we're talking about how we're going to allocate our addresses, each host in a network has to have a unique address. If you have two hosts with the same address, packets are going to get sent to both places, and it will confuse everyone else on the network. So without planning, documentation, addresses could be assigned to more than one host. That'll end up with issues on both of those hosts. So we want to give out those static IPs when necessary. We want to assign them IP addresses. We want to monitor our security and our performance. So when traffic is examined for a source IP, it's generating a whole bunch of packets on the network. We want to have the proper documentation so that we can say, I know where to go find that PC or that workstation, however you want to word it, and go figure out what's wrong with it so that I can fix it so it doesn't have a detrimental effect on the whole network. We can assign IP addresses to our devices. Depending on the device, that may look a little different. So most of our end user workstations are going to have DHCP, give them their IP addresses, because we don't particularly care what IP address they get as long as they get one, so that they connect to everybody else on the network. So normally those are leased for a period of time, let's say 3 days. It's not always 3 days, that can be set. So at the end of 3 days, it's going to reach back out to the DHCP server and ask for another address, or make sure that its current address is not used by anybody else. Your servers and your peripherals should have a static IP address so that you always know where to go to get it. Servers that are accessible from the internet are going to have a static IP address, just like a web server. So if you're typing in tstc.edu, you're calling up the server that holds tstc.edu, and that address needs to stay the same. Okay? The same for a security system. If you have a business and you want to be able to log in and see your security system, your business has to have some outside IP address that stays the same, so that you can always go dial into that address and be able to see the network. You've got your intermediary devices. Sometimes those are used for network management, monitoring, and security, as we saw in the previous slide. But we have to know how to communicate with them, so those need to be static as well. Your gateway, that's your way to get outside of the network. They're generally going to have the lowest or the highest address in the network. It's really, really common to see a router have the address, if you're on a Class C network, to see it say 192.168.1.1. And that is your IP address to get to the default gateway. So that's very, very common. So when we're developing these IP address schemes, generally it's recommended to have a pattern to it, have a flow to it, and not just assign things randomly. Maybe each kind of device or each part would have that. So when you do your packet tracers in this section, you're going to see that kind of come to life. Now let's talk about IPv6. We talked about subnetting IPv4, and we saw the process behind that the last time we met. The good news about IPv6 is it's so much easier. So much easier. So we're going to talk about how to do that. For IPv6, we have what's called a global unicast address. So that's broken down into a few parts. We have the global routing prefix. So that's the thing that's given to you by your ISP. That's the part that every single address starts with those 48 bits. Then we have 16 bits that are the subnet ID. So that is the only place where you subnet, is right there in that subnet ID. And I'll show you how we're going to do that in a second. The organization gets to do that part. And then we have the interface ID, which is the unique part of the IP address that's normally based on your MAC address. And there's one of those for every NIC that's connected. So we have 128 bits, and this is how these bits are lined out. In IPv6, generally we call this section, the first 48 and the second 16, the /64 prefix, because 64 bits of it are going to be may not be unique. These will be the ones, the interface ID, that are unique. So when you're subnetting with the subnetting ID, or the subnet ID, all you're doing is incrementing the field by 1. That's all you have to do to subnet with IPv6. It is so easy. And when you think about it, because you still have 64 other characters over here, you have a whole bunch of addresses in each subnet. Right? In fact, you have, by incrementing that subnet ID, you've created over 65,000 subnets available in that address. So you can see that we would go 0 through 9, and these are hexadecimal numbers because they're IPv6. Then we would go A, B, C, D, E, F. What happens when we hit F? F is the maximum number for that, right?
It's A1,
We're going to move to the next digit, right? And what's that digit going to become? 1. Right? We've run out of things in this digit, so we're going to start with 1, 0, 1, 1, 1, 2, all the way 1A through 1F, and move over when we need to. So you're going to have a packet tracer that's going to show you that. So you will get that in real time.
So when you hit A, it'll be A1.
Hit A, it would be A1.
Then you go down
Yes.
A1.
Yes. So if we're incrementing, let me show you. See if we let me right on it. No. It's finished. Okay, so this gives us, if we go by this scheme, we get 16 subnets, right? So the fourth octet is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They show up as A, B, C, D, E, and F, right? So those are the values that they actually look like. So 0 through F. So then what happens in the third octet when we change over? This is in hex and binary, it looks like this. That might help more. So you've used up all the things here. So this is equal to 1, 0 in hex. You'll have a packet tracer that will show you that. So if you don't understand that right this second, that's okay. But each digit that you see there represents 4 binary bits in IPv6. And I know that's kind of weird to wrap your head around. I know it is for me. So that's how I would represent 16. Or, sorry, 17 actually. The 17th subnet, which is 16, because it goes 0 through 15. Okay, so we have over 65,000 subnets to choose from just by incrementing by 1 in IPv6. So that becomes the task of the administrator to come up with something logical that makes sense. Now we're not allocating addresses and trying to use every single address and not waste anything because we have so many addresses. So, in figure 1 that you can see up here, this will require the subnets for each LAN as well as for the WAN link between 1 and 2. So we need a subnet for that as well. So we're not going to subnet that any further. It doesn't matter that we only need 2 addresses in this instance. We have so many addresses, we'll never run out. So we're not really concerned about wasting those addresses. So when we subnet, we have the subnet ID field, and this is the part that's saying these are all the addresses on this subnet, these are all the addresses on one, because again, we're just incrementing that field. So this, we would refer to this as the /64 prefix, and each one of those subnets will provide way more addresses than we could ever possibly use in this instance. So when you put these addresses on the LAN segments, and in between, this is what it looks like. So you see they got the 0001, they got the 0002, the WAN link between got 0003. Now they only need 2 addresses, so there's over 65,000 addresses wasted, but we're not concerned about that with IPv6. They got the 0004 and the 0005. So all the devices on there are going to have that similar subnet ID in that field. So when you actually put this on a router interface, this is what you get. So when you're talking about IPv6, as I'm sure you saw last week, you have to specify that you're putting in an IPv6 address when you do that. And you're also, when you're here in the console, you're going to refer to it as a /64 at the end. When you're actually putting it in the IP configuration settings, like in a PC, in Packet Tracer, there's going to be a separate field where you can put 64 and it will have a slash there already. So this is what this looks like. We're assigning interfaces with IPv6 addresses, including our serial interface. So in IPv6, we aren't entering a subnet mask, we're just putting in a prefix. And it's gathering from that information. This is what we're supposed to do. In IPv6, we would put in an address and then we would have to put in a subnet mask behind it. With IPv6, we don't have to do that.